Okay, I've just pressed record, so welcome back. This is a tutor-led tutorial. I'm Chris Tisdale, and today we're going to be talking about calculus. Some questions from Chapter 2 and Chapter 3. So feel free to come in on that chat button. Let me know what you're thinking with your questions or with your ideas. The list mostly involve limits and continuity, the list of questions. So I'm going to start with those and we can work through them together. And if you have a question, just stop me in the chat and we can talk about it. So I'm super excited to be back with you. So let me just share the PDF of the question. So this is in the calculus course pack notes, and one of the recommended questions this week is question 12. Okay, so I thought I would talk about part B, and we're asked to compute the left and the right hand limits of this limit here, and then to make a decision on whether or not each of the following limits exist, and if so, find their values. Okay, so this is just a question to kick off today's tutorial, and we'll discuss it. Okay, so let me share something else with you now, because as you know, I do like GeoGebra. So what I like to do with these questions, whenever I can, is to sketch these functions. So here's the function up here, and we are asked to compute the left-hand limit as x approaches 2 and the right-hand limit as x approaches 2. Okay, so from that graph, does the limit as x approaches 2 exist? Does the limit as x approaches 2 exist? It's a yes or no question. Lots of no's coming in. All right. Well, you're absolutely correct. Rosie, the left-hand limit exists, the right-hand limit exists, but they're not equal. Okay, so who can tell me from the graph, what is the left-hand limit as we approach 2 from the left? Who can smash that chat button? What is it? Yeah, thank you, Ning Shao and Brendan, Isabella, Troy. Yeah, -4. And what about from the right? If we approach 2 from the right, what is the curve approaching? Yeah, it's approaching +4. Thank you. So obviously those two values are not equal. So we know just from the picture that the limit does not exist as x approaches 2. But how do you do that in a sort of in a sensible way if you need to write it down? Okay, so let me share what you might do if you're actually writing this this question down. So let me share my Chrome tab. Now I'm using new pens today. I've got a Sharpie. So let's see how that goes. All right. So this is question 12. Okay, hopefully that looks a bit better than last time. Okay, so the question is, if f of x is defined, and I'm just using these dots to define it, is defined like this. Okay, and remember, definitely x can't equal 2. Then let's consider what happens as x approaches 2. Now we know from the graph that this thing doesn't exist, right? But let's actually go through it and work it all out. Okay, so one technique here is to simplify the function as much as possible. Okay, and we'll do that by breaking up this absolute value sign. Okay, so if I move over here, I know with the absolute value that this thing is itself when the thing inside is greater than or equal to 0, and it's negative of what's inside the absolute value signs when the thing inside is negative. Okay, so all we really need to do is solve this, and then we've got two parts of our function. Okay, so where can we solve x squared minus 4 is greater than or equal to 0? So let me draw a quick sketch here. Now, you don't have to do all of this, of course, but I'm just trying to explain it at the same time. Okay, so this green curve is the graph of x squared minus 4, right? And so there it is. And the negative one, where is that? Above the x-axis? Well, it's here, and it's here. And for here, that's the interval here. Okay, so we want x less than or equal to -2 or x greater than 2. And for this bit, where this is negative, it's there. So we want that bit. Okay, now one of the things we need to be careful of course, is this thing here, right? X can't equal 2. Even though this is all correct, we want to exclude x equals 2 from this thing. We'll do that over here. Okay, so let's work it out. So I'm going to break this up, similar to what we have here. So in this region, we'll have x squared minus 4 on x minus 2. And I don't want x to be equal to 2 here, so I'll just make that change. And this part is here. Okay, so we are making progress. Now we can just simplify, right? X squared minus 4 on x minus 2, well, you can simplify that because you can factorize. And you're going to get x plus 2. So you just factorize the top and simplify. And down the bottom, you can do the same thing, except you've just got a negative sign now. So you'll get something like that. Okay. So now we're taking a long time to do this question, but now we can actually take these left-hand limits and right-hand limits. Okay, so well, let's take the left-hand limit and the right-hand limit. So as we approach 2 from the right, that's when x is greater than 2. So we want this function, not this one, this one. Okay, so you can put 2 in there. And let's approach the limit from the left. Okay, so x is less than 2 there. So that's the function you want. So again, these are nicely behaved functions, so you can just substitute in the value. And you can see that the two limits are not equal. So we can conclude since our limits are not equal, the combined limit does not exist. Okay. Oh, what a long question. Okay, you can see here that, well, we really had to do quite a lot of work there, some algebraic manipulation, taking the limit separately, whereas looking at the picture from GeoGebra was much, much more simple, okay? Was much, much more simple. Yeah, so questions, hit me with questions, people. Earlier this week, people were asking in the chat, oh, do I always need to draw a graph? The answer is no, right? The answer is no. And the reason I like drawing graphs, say here, and with GeoGebra, is it helps me understand the problem, okay? It helps me understand the problem. So it's up to you. And do I need to write all of this? Well, probably not. Probably not. I'm just trying to explain it and solve it at the same time. Okay? All right. So that's a standard question. And remember, in your final exams, for example, you will have Maple. So if you want to sketch these curves using Maple, that's quite okay. That's quite okay, because it helps. If it helps you understand the problem, then why not? Why not use Maple or GeoGebra or whatever? Okay. All right, let's press on. Let's do something else. All right, one of the other questions, and I'll put up my PDF. One of the other questions is here. It's number 15, and it's a limit question. And some students, they freak out because they see this. They see the H and they go, oh my goodness, I'm freaking out. That's a hard question. But actually, this question really isn't that hard. So I thought we could discuss it. It's one of the recommended problems. And I'll do what I did in the previous question. And I'll first of all, I'll draw a picture. Okay. So let me go back to GeoGebra, and we can do a little bit of graphing. Okay, so let me just put this in. Cosine 1 on x. Okay, wow, look at that. Okay, so you can see what's happening. So as x approaches 0, you kind of get this sort of infinite oscillating function, and the graph is sort of infinitely oscillating. And it's not clear really what's going on there. It's just a bit messy. Okay, so how do we solve this problem? Well, the graph helps a bit, but let's see if we can do it by hand, and let's see how we go. Okay, so let me share my document camera. Okay, so here is the question. This is number 15 now. Okay. The question is, compute the following limit of cosine 1 on x as x approaches 0. Okay. All right. So one strategy here is, instead of considering the whole limit, let's just consider, say, the right-hand limit. Okay. So let's consider this right-hand limit, because that will help us understand the limit in general. Okay? All right. So it's not very clear what's going on, but things become clear if you consider a substitution. So substitutions can help you in calculus and taking limits and things like this. If I let u equal 1 on x, then this thing immediately simplifies, right? And the only thing we need to be concerned about here is what happens to u as x approaches 0 from the right. So if I have, say, a graph like this, and I put in, oh, let's use orange. Okay, this is like u equals 1 on x. Then as we come in towards 0 from the right, what is the curve, the orange curve approaching? Who can tell me in the chat? If I come in from the right here towards 0, what is the orange curve approaching? Who can tell me? Yeah, it's increasing to positive infinity. So okay, so now let's reformulate this in terms of a limit involving u. Okay? So we change the thing we're approaching with u going to infinity, and cosine 1 on x will just be cosine u. Okay, so here is the big question. 3:22 p.m. in Sydney. What is this limit? Who knows? Who can tell me? There's 70 people here. Who can tell me what this limit is? Anne says infinity. Tom says no limit. No, 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 no. There's no limit. Liz says it just keeps oscillating. Oh, Anne's changed. Okay. Sartak, undefined. Oh, Ning Shao says 0. Juno, -1 to 1. Well, I think you've all got good points there. This, I'm sure you'll agree, this is a much easier limit than this, right? But and they're the same. So if we can understand the cosine function, then, and what happens to cosine as its variable gets large and positive, then we can solve this problem. So let's go back. And what happens? People have been saying this, it oscillates. And it just oscillates. Yeah. And it oscillates. And it doesn't approach anything, right? It's a periodic function that repeats itself. And it doesn't approach anything. So the limit, as a few people have pointed out in the chat, the limit does not exist. Okay, it does not exist. So let's write that down. Which does not exist. So if this and this are the same, and this one-sided limit doesn't exist, this original limit absolutely cannot exist. Okay, it cannot exist because this only exists if this and the left-hand limit exist and are equal. Okay, so this limit absolutely cannot does not exist. Oh, it's having a crisis, an existential crisis. Oh, I don't exist. Oh no. Oh well, it's okay. Yeah, Eleanor, it does stay as a wave. The cosine function, it just repeats itself over and over again. It's periodic. So you're absolutely correct in the chat. Okay. So they're the recommended questions from chapter 2. Why don't we move on to chapter 3? So I'll pull up the PDF for that. Okay, so just give me a second. Chapter 3 is mostly about continuity, max-min theorem, things like that. So let me share that. I'll stop sharing here. And let's take that up. Okay, so this is page 60. We're only supposed to do up to 3.3 in this problem set. So I'll actually start with question 1. It's a pretty easy question, but I think it's good to understand and good to discuss. Okay, so we've got a function f. It's real valued and it's defined by the absolute value. Show that f is continuous at x equals 0. And then, is f continuous everywhere? Give brief reasons for your answer. So the first part is asking you to show that f is continuous at a point. And the second part is asking you, is it continuous for all the points in its domain? Is it continuous on the whole line, whole real line? And do some justification. Okay, so let's have a look at that. I've got my GeoGebra ready to go. So here it is. Here is my function. So who can tell me in the chat for part A, is this function continuous at x equals 0? A few yeses, a few nos. Keep them coming. Well, remember, a function, the graph of a function, if you can draw it without lifting your pen or pencil off the page, then it's definitely continuous. Okay, there's no jumps, but this curve is continuous. A few people in the chat have said, oh, well, down here, it's got a corner or a spike, and so it's not differentiable. Yeah, that's true. That's absolutely true. But it is a continuous function. Okay, not only at 0, but it's continuous everywhere else as well. Okay, so let's put that into words. Okay, and let's put that down on the page, and we can see how we actually do it. Okay, so we have a function, and this is question 1 from chapter 3. So Here's our absolute value function. And we know that this is a piecewise defined function. It's got two parts to it. And this is basically the idea behind the absolute value. Okay. And we've got a curve like this. Let me use orange. This is like negative x, and this is positive x. And the first question is, well, is this function continuous at x equals 0? Well, we know from the graph that it is, right? But let's actually, I think what they want you to do is to use limits here, okay? So let's work out what the condition for continuity at a point is. We want the limit to be equal to the value at that point. Okay, so what's this? This is composed of two parts, left-hand limit, right-hand limit. So on the left-hand side of 0, we're going to have negative x. On the right-hand side of 0, we're going to have positive x. They're obviously heading in the same towards the same point. Okay, so we know where we're going, but let's do it formally. So when x is coming in from the left, it's below 0, so negative x. That's just that. When x is coming in from here, from the right, it's greater than 0, so that would be my definition. Finally, what is f of 0? Well, when x equals 0, it's just x. And you can see all of these three things are equal. Okay? And so f is continuous. I'll just abbreviate that at x equals 0. Okay, so second part of this question. Is f continuous for all the x points? And if you were solving this question, what would you write? Okay, what would you write down? How would you justify it? I can see Nabil has always talked about smoothness and differentiability. Sartak has talked about continuous but not differentiable, which is all good. But in part B, is f continuous everywhere? In other words, for all x points. What would you write down if you were solving this problem? Let me know in the chat. What would you write down? Smash that chat button. Let me know what you're thinking. Okay, so yes, it's continuous, and how would you justify it? So Ning Xiao, you're absolutely right. Okay, keep the chat coming, people. I'm loving it. Eleanor says, have to find if there's a point that can be divided by 0. Is that right? Ah. Hara is saying continuous for all points. George is talking about infimums. That's interesting. I think there is a simple way of talking about the answer to this question. Okay. The parts of your function, they're polynomials, right? In fact, these are just linear functions, and they're always continuous. And the only potential problem is where the the function changes from this type of function to this type of function. But part A told us f is continuous at x equals 0. Yeah, Ningxia, now you're right. Polynomials are always continuous. Okay, so if I was answering part B, what I would say is the following. Okay, I would say something like this. We have polynomials in our piecewise or split function. And polynomials are continuous everywhere. So a polynomial is just something like a linear function, quadratic, a cubic, a quartic, these sorts of things. So they're very friendly functions. Also, f is continuous at x equals 0. Together, this means that f is continuous everywhere. Yay. We're happy about that. Okay, so when it comes to your writing assignment, you will be expected to write sentences like this or type them up. Okay, so yeah, Liz, you're on the right track in the chat. Y equals x is a continuous function. Y equals negative x is continuous. So the only part where it changes is here, where it goes from negative x to positive x. So you have to worry about that point. But part A takes care of that. So you're absolutely right, Liz. Thanks for that. All right, keep those questions coming. Let's move on. We continue. All right. So let me go back to GeoGebra. Actually, no, I'll go back to the PDF. All right, so we answered part A and part B in question 1. Question 2 is also in this list. Determine at which points these functions are continuous and give reasons. All right, so I'll do part A. I think that's an easy one. Once you've done part A, part B is pretty easy to understand. Okay, so you've got a piecewise defined function or a split function, whatever you want to call it. And it involves an exponential and a trig function. And the change happens at x equals 0. Okay, let's work out the continuity of that function. Okay, so you know what I'm going to do, go back to GeoGebra. Of course, you don't have to draw pictures or use GeoGebra, but I find it useful when you can do it. All right. Ba-bow. So there it is. Okay. All right, so Adita in the chat has a good question. What does this mean? It means that f has the domain of the real numbers. Yep, and it outputs a real number. Okay. So that's what it means. If you can put any real number into this function and you'll get out a real number. Aditi, does that make sense? Yeah. Sometimes the notation is a bit strange. Okay, so here it is. Here's my split function. Ba, ba, ba. You can see the change occurs at x equals 0, and it almost looks like there's a wave traveling and it's about to break here, right? Almost. But you know, there it is. So looking at that graph, is this function continuous at x equals 0? Let me zoom in. certainly looks like it's continuous. Okay, there is a corner there, but doesn't matter for continuity. Thank you, everybody. I think you're right. And so that's the first part. So it's definitely continuous at x equals 0. What about everywhere else? Is it still continuous everywhere else? Who can tell me? Yep, lots of yeses there. Absolutely correct. So this is a split function that is continuous at all points in its domain. Okay, so let's think about how we can write that down. We know it's true from the picture and the graph, no problem. But let's see how we can write it down. So let me share my Chrome tab. All right, so this is 2a. All right, so let's consider, please, this piecewise defined function. It's an exponential function when x is negative, and everywhere else it is the cosine function. Okay. All right, so let's break this down into two parts. We kind of know where we're going, but let's just do it anyway, right? The first question is, so let's claim f is continuous at x equals 0. Okay, so let's verify that by working out the value. What is the value of f of 0? Well, when x equals 0, we're here, right? So it's cosine function, which is 1. And let's take the left-hand limit and the right-hand limit as x approaches 0. So as we come in from the left, that means x is less than 0. So it's this function here. And because this is a nice friendly function, we can just put in that. So that and that are the same. So that's looking good. And let's approach from the right. So when x is bigger than 0, my function is the cosine function. And again, you can just put the 0 in there. Okay, so we got this, this, and this. So now mathematically, from a calculus point of view, we are convinced that this is continuous at x equals 0. And so let's make a final line here. All right, last part. What about everywhere else? So e to the 2x is continuous everywhere. Cosine x is continuous everywhere. So, you know, we put those together. So combining the above we see that f is continuous everywhere. Oh, okay. Now, I've written a lot there, but like I said, I'm trying to explain it and also solve it at the same time. Okay. Okay, so questions. Keep that chat going, people. If people have questions or I'm not being clear about something or anything like that, please feel free to smash that chat button. Okay. Let's do one more. Okay. I'll just draw a picture here. Let me go back to Geo. Oh, actually, I'll show you the PDF first. Okay, let me show you the PDF. Okay, so here is question 3. And you've got another split function. And you're asked to find the values of k such that this function will be continuous at all points. Okay, so what I'll do is I'll actually, oh, shall I do GeoGebra? No, I won't do GeoGebra. Okay, I think we can do it pretty quickly without GeoGebra. So let's have a look at that. And one thing we can do is simplify our function. Okay, so this is question 3 now. All right, so consider, please, this split function. So as long as we're not at 4, this is our function, and it's this. Okay, so this is actually a pretty easy problem. Can anyone suggest how we might simplify this thing here, this expression? Anyone? Anyone? Yeah, we can definitely simplify it, right? Because this is just x plus 4, x minus 4. Okay, so it factorizes, right? Everyone's on the right case. So if I divide this by x minus 4, and I'm not at 4, it means that I can, of course, smash these off. Okay, so we actually have here this. So let's sketch x plus 4 and we can work that out. So at x equals 4, we want to pick some value. So this thing isn't defined at x equals 4. Okay, so let's go up here and okay, this isn't a great picture, but you get the idea. Okay, so at the moment, I've only drawn this part of the function and I've left this open hole at x equals 4. So the question now is, can I plug that hole? And what should the value of the function there be? What should the k value be in order for this whole thing to be continuous? Can anyone suggest a value of k? Yeah. Tom Smith, awesome. So if I was to take my pen and just go bloop, I'm going to define k to be 8, then it's like I'm putting my finger in a hole and plugging the hole. Okay? That's it. Okay? And you can verify that by saying, well, you know, the limit as you approach 4 from the left is going to equal the limit from the right, and they're both going to be 8, and the value of the function has to be 8, which is what Ha is saying in the chat, which is perfect. Nice Bernie pick, by the way. Completely fine. But I think drawing a picture is fine. So let's make a conclusion. I'm just looking at your comment. Nice one, Joe. For k equals 8, we have our f being continuous everywhere. Okay? So obviously a linear function, that's continuous. The only problem is where x equals 4, and we can choose k to plug that gap. Plug that gap. Okay? All right. All right, people. Well, I think that's enough from me today. What other questions do you have about this course or assessment or study methods? Anything? We've got a couple of minutes here, so feel free to hit me up in that chat. Is there something you would like some clarification on, or you know? Then again, I did end up doing week 4 questions in week 3 on Monday, so you know, what do I know, right? Oh, Smith, that's a great question. Practice tests usually come out in maybe week 4. In previous years, you do get a couple of practice tests to practice with, so there will be an announcement coming. Okay, Aditi, we're choosing k to be 8. Okay, they want us to choose a k, choose a value of k, so that this whole thing is continuous everywhere. And you can see from the graph, the only way to plug that hole is to make the value at x equals 4 equal to 8. That's it. Okay, so it's up to us to find a k that makes sure that this thing is continuous everywhere. Okay. Ah, Brendan has popped up. It is already posted on Maple. Brilliant. I didn't know that. Thank you, Brendan and Stuart. Stan, the final exam is usually harder, much harder than lab tests and weekly Maple TA quizzes. So in the final exam, it really sorts out the high distinctions from the distinctions and the credits and stuff. So I don't think you can aim to do every question, whether or not that is realistic. You know, I don't know. I mean, a lot of people get 50 out of 50 for the Maple TA quizzes, the writing assignment, and the 2 lab tests. They get 50 out of 50, and then they take the final exam. Okay, so Tom, I think the lab tests will be in Maple TA. Okay, so they're like, if you log in there, you should be able to find them hiding around somewhere. Okay. Yeah, Will, I don't know if I'd trust those old PDFs because that's before COVID. So I would stick with the ones that are on Maple TA. I don't know if I'd trust those old PDFs because that's before Maple TA was even involved. So they're good practice maybe for the final exam, but not so much so for the lab tests, if that makes sense. Or Stuart, I don't really know. That's a good question, but it's usually it's pretty constant from term to term. So it's not like one term, 90% of the students pass, and then next term 40% of the students pass. Okay, Tom, just read the course outline. The lab tests are 2 Maple tests that are timed and that you do on your computer at home. Okay, Eleanor, I don't think it's graded on a curve, but there are some educational adjustments done at the end. So that's just basically out of fairness to everybody. So it's not like if 90% of students failed everything, then they'd get passed. Like let's say 90% of students got a HD. I don't think that would be scaled down. Yep. Well, it depends on the scaling, right? Depends on the scaling. So some people, some people think they did really poorly and then they're surprised by their final grade. Others, they think they did really well, but then they end up, getting I don't know 70 or something, and they're like, oh, how did that happen? So yeah, there are measures and stuff involved with moderating the marks. Okay. All right, folks, it's time to go. So goodbye. I look forward to maybe a bit of warm-up music next week, and just enjoy the rest of week 3. And I'll sign off. And I'll bring some more toys next week. Somebody was asking about toys, don't worry, I've got you back. All right, thanks everyone. See you.